The second chi-squared procedure we typically learn about is the test for homogeneity or homogeneity, however you choose to pronounce it. So here are some data from last year. The important piece being our question here. It's the wrong section with the new book. But is the distribution of gummy bear color the same for these two different brands? And this is a Statmetic activity, so they used Haribo. And then I bought Giant Eagle because that's this, equivalent to a Myers brand. So collecting data and seeing what happened. So this was what the breakdown was. We had to adjust our colors a little bit, but 5 basic color categories. The observed counts we had in each one, so that's why the bold lines are marking them off. The totals are there, but we don't use the totals whenever we are working through our test statistic calculations. It's the observed and expected, just like it was with goodness of fit. So my hypotheses, again, are much easier to do in words. So my null hypothesis being that the distribution of gummy bear color is the same for Haribo as it is for Giant Eagle. And my alternative distribution, my alternative hypothesis is that the distributions of gummy bear colors differ. And so they're either the same or they're not. And that's what it means to be homogeneous. And so those are my hypotheses. My conditions, again, random independent and my large counts. So random and independent, again, sometimes a little rough as we're collecting class data. And also to not review those because we've discussed those already. And so random and independent. But it's our large counts condition now that we are interested in. So my large counts, again, is that my expected counts are all at least 5. And so what happens with this one, first, if you take a look, there is a 3 that happens to be here. But we're not concerned with this because it's an observed count, not an expected count. We could have had 0 in any of those categories and it would have been okay. So we don't quite have a 50-50 split here with our 63 versus 54. If we did, then it would just break down proportionally by the 5 different colors that are there, which is also not the same. So for instance, this is probably our closest one. We have half as many yellows as we do red and purple. And so taking those proportions into account and what the breakdown should be, and then figuring out what each of my values are. So if I look at just my first expected count, my red and purple, this one does have a new formula for us. If we think, there are 63 of my 117 Haribo gummy bears that make up this table. That breakdown, then, it's essentially weighted so that the Haribo should have as many. So this 63 out of 117 is equal to about 54%. So it should be 54% then of each row that also breaks down so that it's weighted. So 54% of the 39 tell me that I should have 21 red Haribos and I had 20 for what was given. So it's not terribly far off from what was expected. Now that obviously won't be the same for some of the others as we work our way through. But that's what the breakdown is doing with expected count. So it is looking proportionally at the row or column. So I did column total, my 63 out of my table total. and then converted that back into a count by looking at the row total to see how that would break down. For ease, for whatever reason, it's usually the row total times the column total divided by the table total as the formula that's given to us when we look at them. But again, I think it makes the most sense if you think of them proportionally how they break down. So looking at this marginal distribution that we had here and recognizing that that percent should match. So imagine how tedious this would be to do this for all 10 different components that we have. So there's a little bit of a cheat here that we typically get into. I usually backtrack to my conditions and I do my work step first. So my chi-squared statistic is still going to be the sum of all of my observed minus expected counts squared over expected. So it's the exact same for all three of my tests. I'm going to find this on my calculator first. Whenever we run this chi-squared test in the calculator for the homogeneity and for the association, we still have to talk about. The calculator automatically finds all of your expected counts for you, so you don't have to go through that tedious process on your own. So if you go to your calculator, we haven't used them before, but we're looking at matrices. So from the home screen, just go to second matrix, and then you need to choose to edit. And I typically just use A. And so it's a 5 by 2. It's 5 rows by 2 columns. And if you don't remember much about matrices or have experience with them, when you put the dimensions in, it automatically builds it in the calculator so you can see if the dimensions will match what you have in your table. So here are all of my observed counts that I used. So if I go to stat tests and go to just the chi-squared test, not the goodness of fit test, this also operates in a different way. It's really asking me of an input-output. So my input is that my observed counts were in A. My expected is that it's going to put them in B. And so if you looked at my matrix menu, there weren't any dimensions listed next to B, which means I have nothing stored there right now. So whenever I hit calculate to get my test statistic and p-value, 9.87 for my test statistic and that p-value of about 4%, this is going to, when I go back to my matrices, generate for me this 5 by 2 matrix that's here. And so if I take a look at my 5 by 2 expected counts, I can see that all of these counts are in fact at least 5. And so we do typically have to go through the process of jotting them down. I took a screen capture of all of this from the old one, so I didn't have to toggle back and forth. So all of these expected counts here that are listed are in fact greater than 5. And so this condition is met just by showing that work. So if you had taken those expected counts and put them next to the observed counts and said to refer to that table, then that would work for showing those particular values. My work step still, if I'm looking at my chi-squared, my test statistic here, I still want to show really first and last. So I had 20 of the red Haribos and I was expecting 21. So 20 over 21, sorry, 20 minus 21 squared divided by the expected count of 21, all the way up to my last count. We had 8. And so 8 minus that 8.3 squared divided by 8.3 is where my 9.871 comes from. So again, not really a very big number, and I have 10 different components. Now, if you wanted to do the follow-up analysis, matrix operations don't work in such a way that you can take observed minus expected and square it, and then divide by the expected matrix. So you could convert this into just an ordered list of the 10 values that are there. Say have all 5 Haribo first and then all 5 of the Giant Eagle brand. And then do the same thing with expected counts. And then it would be similar to what we did yesterday with goodness of fit. Just list 1 minus list 2 squared over list 2. The p-value is automatically given to us by the calculator, but something else that is new besides the expected count are the degrees of freedom. So my dimensions for this table are 5 by 2. I have a note here, the screen capture from last year, that the degrees of freedom are row minus 1 times column minus 1. And that is because if I were to take this table and have my 5 values, if I know I'm supposed to have 39, 28 the whole way through, and then I'm supposed to have 63 and 54, if I think in terms of freedom, if I were to fill this table with a particular value, how does that force anything else into place? So let's say that I had 30 here instead of the 20 and the 21 expected. That would force this to be 19. And then I could put 20 here, and that would force that to be 8. I could put 10 here, and that would force it to be 9. I could put 10 here. Now I'm done, because this is forced to be a 3. This is forced. This is forced. So I had these 4 that I entered on my own, just making numbers up to see if they would fit so that I had the appropriate row totals and column totals. So essentially, it's everything but the last value, because it would be, if I have 5 things, if I know 4 of them, I know what the 5th one has to be in order to reach that total. So you lose a row, and then you lose a column, and it's whatever is left. And because we're dealing with a table like the 5 by 2, those values just get multiplied. We often have only 2 columns. And so it tends to be 2 minus 1 whenever we're working through, but it doesn't have to be that way. So we ended up with a p-value that's right on the cusp here. And just for the sake of remembering, I'm going to say we do not have enough evidence to reject the null hypothesis because it is less than 5%, but it's not less than 1%. So we do not have enough evidence to reject the null hypothesis at a significance level of 0.01. And so if we were to use that stricter level for whatever reason, we fail to reject. And so assuming the gummy bear color distribution is the same for both Haribo and Giant Eagle, we would see proportions such as ours. And that's just a blanket because some of them might be more than expected, some might be less than expected. So it's not really a one-way or a two-way test. It's considered a many-sided test. So just recognizing that proportions such as ours are that different. About 4.265% of the time. So again, just for a review, I chose to not reject the null hypothesis because the p-value is less than the alpha level. Assuming the gummy bear distribution, that second sentence would be exactly the same, even if I had said I was rejecting it at the 5% level. Because my first sentence is just making the decision and tying it to the significance level. The second sentence is putting it into context, interpreting that p-value, which is the same for all of our tests, no matter whether we're talking about chi-squared and proportions with z's, or if we're talking about means with the t-test. So, a lot of jumping around. Just to rehash, we are given the observed counts. We write our hypotheses in words. If it's homogeneous, they're the same. If not, it is different. One of the pieces I didn't mention at the top, these came from 2 separate populations. So Haribo is considered separate from Giant Eagle. And having those 2 is one of the distinctions between the homogeneity test and the association test. So those 2 being the same or being different. Conditions, the only thing that's new is that the expected counts take a little bit more to calculate, but the calculator does it for us. The work step is the same as what it's been. The conclusion step is the same as what it has been.